So let's define formally what a Turing machine is. So we have a control mechanism, a finite state control, which you can just think about it as being a DFA or an NFA, depending on the exact model of Turing machine we are thinking about. And then it has a head. The head can read and write from the tape. The tape is one-sided, so you can think about it as array numbered 0, 1, 2, and so on to infinity. The input initially is written on the beginning of this array or the beginning of this tape until you reach the end of the input, and then you just have blanks, which are this special marked space character all the way to infinitum. And now in every step of computation, the Turing machine reads what's written on the cell of the tape, or the squares, as Turing called it in the original paper. Reads what's written in the cell and does a transition according to its current state, write potentially something new on the square, and then move the head either left or right or stay where it is. Okay, so that's what a Turing machine is. So clearly, for example, a DFA is very easy to simulate, right? It's just a Turing machine that always go right and stop once it arrives to the first blank. An NFA is just, it's a bit harder to simulate, but in fact, we will get later on, but it's in fact not too hard to simulate with this model. Okay, so that's a Turing machine. So what are our goals here? So what I'm going to try and convince you in this lecture is that Turing machines are equivalent to regular programs. Right now, I'm going to give you a few examples, but I'm not going to go very far because programming Turing machines is as enjoyable as programming in assembly, which is not enjoyable at all, and hopefully most of you never did it. So it's very low level and it's very painful and very tedious. So I'm going to point out a few examples and give you the general feeling. And then if you're interested, you can verify that you can, in fact, do any program can be converted into a Turing machine. Right. So in particular, the Church-Turing hypothesis or the Church-Turing thesis was that all computers are equivalent to a Turing machine as far as what they can compute. Right now, this is not a claim that can be proved or disproved because it's kind of a general mumbo jumbo claim. But so far, we don't have any counterexample. And in particular, quantum computer, even if they're real, which remains to be seen, are not going to, of course, contradict this, right? So this thesis seems to hold quite well. And the nice thing is that if you have the Turing machines, they're really simple if you compare them to a computer nowadays, right? Just think about the mind-boggling complexity in a modern CPU, right? You're talking about something that have hundreds of millions of transistors, insanely complicated. Nobody really understands what exactly is going on. The only way for a modern program to know how well, how fast it would run on a computer, on a CPU, is just to run it, because there are so many complex issues with several level of caches and pipelining and so on and so forth. So you have these extremely complicated modern computers, and on the other hand, you have a Turing machine, which Turing machine is simple and we can argue about, and they're equivalent as far as what theoretically they can compute. So that's the benefit of Turing machine. It's really a clean, simple model, relatively speaking. And one of the things that we will need to talk about is universal Turing machine. And that's somehow if I had to give, the important things in Turing original paper, the universal Turing machine was the real breakthrough, right? And that was the observation that you can essentially, a program can run another program, simulate another program, namely an interpreter, and which is a very powerful ability. And this will give us various implications about what can be computed, what cannot be computed, and so on. Okay, here is the formal definition of Turing machines. I'm sure you were waiting happily and anticipating this exciting new definition. So it's the usual tuple nonsense. So let's go through the stuff. Don't worry too much about all the stuff. So you have a set of states. You have an input alphabet, that's the input that is. There is gamma, which is the alphabet written on the tape, which is a superset of sigma. There is the delta, the transition function, which is going to be a mess, of course, because everything is going to be a mess. There is a start state, which is where the start is. And then there are two special states, accept and reject. And unlike previous models we had, as soon as the control reaches the accept states, the machine stops and accepts. As soon as the machine gets to the reject state, it stops and rejects. Okay. And then, as I mentioned before, there is the special space characters that are the infinite, that all the empty cells of the tape are filled with. Okay. Next. So the promised transition function. So the transition function is a function from the current state and the current letter written on the tape where the head is, and the result is the new letter to write on the tape. The new letter to write on the tape, but more importantly, the state to move to. And finally, you also need to tell the Turing machine what to do with the head, whether to move left or right or stay where it is. Okay. So in particular, delta Q of C, if we will write down it equal to PDL, which means that from the state Q, it moves to the state P. The letter C on the tape, that is the current letter under the tape C, is being replaced by the letter D. And L means that the head is being moved to the left. Okay? And as usual, it's much easier to just draw it as a state diagram. So we write it as like this, right? So the letter C is replaced by the letter D. The transition is from Q to P. And L means the head moves to the left. Okay. So that's the transition function. Okay, importantly, if the Turing machine, the head moved to the left past the beginning of the tape, then, you get, the machine crashes, right? You get a blue screen of that, or, the ghost of Turing comes and stabs you in the back or something. So it's a bad thing and it shouldn't happen. Okay, that's it for now.